Okay, let's dive right in. We're going to break down one of the most fundamental ideas in all of machine learning. It's this constant tug-of-war, really, a battle between getting the big picture right and not getting tricked by all the random noise. It is a true balancing act.
You know, everything in machine learning really just starts with a question. A lot of times, it's a question about what's going to happen next. So, for example, imagine you own a gelato shop in Rome. You'd probably love to know how much gelato you're going to sell next summer, right? That's a prediction problem.
And to answer a question like that, you've got to figure out the relationship between different things. For gelato, it's pretty obvious, right? It's probably the temperature outside. The hotter it gets, the more gelato people buy. The whole point of what we call regression analysis is just to capture that kind of relationship in a mathematical way.
Now, the way we do this is by using something called a model. And I know that word can sound a little intimidating, but a model is really just a formula or an algorithm that tries its best to copy that real-world relationship. It's like our attempt at building a crystal ball.
Okay, let's make this a little more real. Forget gelato for a second. Let's try to predict a car's fuel efficiency, its miles per gallon, or MPG, just based on its weight. I mean, just look at this table for a second. You can already kind of see a pattern, can't you? The heavier the car, the lower the MPG seems to be. So to capture that pattern, we can use one of the simplest models in the book, a linear model. And all this fancy-looking equation really is the formula for a straight line. That's it. Our job is to find the one single line that best slices through the data points we have.
So let's break that down. Y prime is just our prediction, our best guess for the MPG. X1 is our input, the car's weight. The two things the model needs to learn are W1, the weight, which is really just the slope of our line, and B, the y-intercept. Now, in this equation, B is called the bias term, but hold on. Try not to confuse this with the big concept of bias error we're going to talk about in a minute. They're different. W1 and B are the model's parameters, and learning is just the process of finding the absolute best values for them.
Okay, so we've got a model, and it's spitting out predictions. But how do we know if it's any good? I mean, are the predictions great, or are they terrible? We need some way to keep score, to actually measure its error.
A really common way to do this is with something called mean squared error, or MSE. That sounds super technical, I know, but the idea is actually pretty simple. For every car, you just look at the difference between what your model guessed its MPG was and what it actually was. You square that difference just to make all the errors positive, and then you average them all up. The lower the MSE, the better your model is. A perfect model, that would have an MSE of 0.
And this is where it gets really interesting. That MSE number, that total error, where does it actually come from? It turns out it's not just one thing. It's actually a mix of a few different and sometimes competing sources of error.
To really get this, we need to kind of pop the hood and look at the anatomy of that error. We can actually break down our total error into 3 core pieces, and I promise, understanding these is the absolute key to building better models.
And here they are. Our total mean squared error is basically made up of bias, variance, and a little something called irreducible noise. Now, that noise part, that's just the random static that exists in any real-world data. It's the stuff no model, no matter how smart, can ever predict. The parts we can control, though, are bias and variance.
All right, first up, bias. Bias is the error you get when your model is just too simple for the job. It's making the wrong assumptions. Think about trying to describe a really complex curvy relationship using just a simple straight line. It's never going to be a perfect fit, right? The model underfits the data. It's just not flexible enough to capture what's really going on. It's systematically wrong.
Here's a great way to think about it. A high bias model is like an archer whose sights are off. They might be incredibly consistent. I mean, they hit the exact same spot on the target every single time. The only problem is that spot is way off in the top left corner, nowhere near the bullseye. They're precise, but they're not accurate.
So on the complete other end of the spectrum, we've got variance. Variance is the error you get from a model that is, well, it's too complex. It's too sensitive. It doesn't just learn the real pattern in the data, it starts to memorize every little random bit of noise too. We call this overfitting. So our second archer, this one represents high variance. If you average out all their shots, they're actually centered right on the bullseye. But look at the target. The arrows are all over the place. One's high, one's low, one's left. Each individual shot is totally unreliable because this archer is reacting to every tiny gust of wind. They're accurate on average, but they're very imprecise. And this right here brilliantly illustrates the central challenge of machine learning.
As you make your model more complex to reduce its bias, to get it closer to the bullseye, you almost always increase its variance, making it more jittery and sensitive to noise. And if you make it simpler to lower the variance, well, then you risk increasing the bias. It's a fundamental trade-off.
So the crucial point, the thing you really have to get, is this. Minimizing your total error is not about getting bias to 0 or getting variance to 0. You can't. It's about finding that sweet spot, that perfect balance between these two competing forces.
So how in the world do we actually find that balance? Well, it all comes down to the process we use to train the model, the method it uses to find the best values for its parameters, that weight and intercept we talked about way back at the beginning.
For a long time, the go-to approach was a method called ordinary least squares, or OLS. And it's this really beautiful piece of math that can solve for the single best line in one clean calculation. But there's a catch. It has to look at the entire data set all at once, which makes it incredibly slow and sometimes just plain impossible with the gigantic data sets we have today.
And that's exactly why modern machine learning has pretty much moved on to these iterative methods like gradient descent. Instead of one giant perfect calculation, it takes lots of small, smart steps in the direction of the lowest error. And the most popular version is stochastic gradient descent, or SGD. It's insanely fast because it updates the model using just one data point, or a small batch at a time. It's definitely a noisier, more wobbly path to the bottom, but it gets you there.
And SGD itself has this really cool history. What started as a pretty simple idea back in the 50s has just been getting better and better. We added concepts like momentum, which helps it power through flat spots. Then came adaptive methods like AdaGrad, RMSProp, and the current undisputed champion, Atom, which intelligently adjusts how big of a step to take for each parameter. All these innovations just help it find that bias-variance sweet spot even faster and more reliably.
So what's the big idea you should take away from all this? Building a great machine learning model isn't about some quest for perfection. It's not about creating a system with zero error. It's about skillfully managing this fundamental trade-off. The whole goal is to build a model that doesn't just memorize the data it's already seen, but one that generalizes well and makes accurate predictions on new data it has never ever encountered before.
And that leaves us with one final, pretty deep question that really goes beyond just machine learning. As we build more and more of these complex AI systems that are shaping our world, what kind of error are we more willing to live with? Is it better for a system to be consistently wrong in a way we can predict? Or is it better for it to be right on average, but with mistakes that are completely unpredictable? The answer, well, it's not so simple.